Hi, I'm Curtis, and I want to talk about unsatisfiability proofs in Lamb's problem. Lamb's problem is a famous problem for mathematics. It was centuries old and finally resolved only with the help of a supercomputer. It has to deal with some mathematical objects known as finite projective planes. I've given you a couple examples on the slide here. These are objects which satisfy some simple axioms, one of which says that on any line there's the same number of points, it's going to be one greater than what's known as the order of the plane. Now, the question then becomes, for what orders do projective planes exist? For example, up to 9, they exist in all orders with the exception of 6. So at 6, there's a theoretical obstruction. You can just completely eliminate this case from consideration. But order 10 is very interesting. There's no such projective plane known, and yet there's no theoretical obstruction from such a plane existing. So you could actually conjecture either way. This problem became known as Lamb's problem after Clement Lamb extensively studied this problem in the 1980s. In fact, with the help of some collaborators, he wrote a supercomputer search which resulted in the negative. However, their code was not verifiable because they never published their code and it produced no certificates, so you just have to trust that the computer did the search correctly. We wanted to put Lamb's problem on a more sound foundation by generating unsatisfiability proofs, which then a third party could verify for themselves actually show the non-existence of the projective plane of order 10. To do this, we employed a SAT solver. These are programs which solve problems in logic, but you can also reduce many other types of existence problems to a SAT problem. For example, take a look at the chessboard here. Say you wanted to color the squares on the chessboard, but repeat no colors in any row, column, or diagonal. It turns out there's no way to do this with 8 colors, although there is a way with 9 colors as shown here. But how would you prove to someone there's no way with 8 colors? One way to do this is to reduce the problem to SAT and then generate an unsatisfiability proof for the 8 coloring. Another type of software that we use is known as a computer algebra system, or a CAS. These are systems designed to do mathematical calculations. For example, if you take a look at these two graphs here, they look different at first. However, it turns out these are actually isomorphic. A CAS will tell you they are isomorphic and actually provide you with an explicit isomorphism that you can check. This brings me to the SAT+CAS paradigm. SAT solvers are really good at doing efficient searches, whereas CAS are really good at expressing mathematical calculations. There's lots of problems like Lamb's problem where you want both. You want the best of both worlds. The way our system works is as follows. The SAT solver is going to be looking through the search and finding partial solutions or partial projective planes. For example, here's a 4.6 line projective plane. You give it to the CAS and it analyzes this partial solution. It says, well, take a look. If I rotate it 180 degrees, I get something which is equivalent. It looks the same. Therefore, I can block it because anything which is derivable from the first solution is also going to be derivable from the second solution. So I can just block the second. And the reason this is so powerful is because every time you spot a new symmetry, you can block more of the search space. In the end, we were able to generate the first collection of non-existent certificates for Lamb's problem. And in fact, we were actually the fastest known way of solving the problem. In one case, we solved a case in 30 hours that took the previous search on a similar computer 16,000 hours. So if you're interested, you can check out the certificates and scripts on our website shown here. But in conclusion, I really want to stress just how general this paradigm is. Anytime you want fast, verifiable, and expressive searches, the SAT+CAS is a great way to go because the SAT solver gives you fast and verifiable, and the CAS gives you expressiveness. Yes, you might have to structure your search in a different way, but the upshot is that you avoid writing special purpose search code. This is code which is hard to write, even harder to make efficient, and almost impossible to verify. Whereas if you use a SAT solver, SAT encodings are typically easier to write. SAT solvers are already very efficient, and plus they provide you a certificate in the end, so you don't have to trust them. For future work, we're really excited to push this to new domains and new applications. So I'm always looking for new students and collaborators. So if you're interested, get in touch, pass on the word to anyone else, and I'd be happy to take any questions at IJCAI. Thank you so much.